Next, we're going to find the magnetic field due to an ideal solenoid. So a solenoid, which is a coil of wire, is something that is often used to make electromagnets. So what we mean by ideal is that we are assuming the solenoid is very long and with coils very close together. That means the magnetic field outside the solenoid will be zero and the field inside will be uniform. So you can see here already where we've chosen our Amperian loop to be, that is going through the sides of the solenoid with one side down the middle of it and one side on the outside of the solenoid. So here is my drawing of a solenoid with just a segment of it there. Along the top, those are meant to be the cross sections of the wires with current coming out of the screen, and at the bottom it's the cross sections of the wires with the current going into the screen. So you can see we've cut right through down the center of the solenoid. Now we have our loop here with A, B, C and D, and the length of the loop is H there. So we're interested in a segment DS as we go around the four sides of the loop. Now we're assuming that the magnetic field is naught outside the solenoid. So our integral of B times ds is going to be from A to B plus B to C, C to D, plus D back to A, B ds, and they all need vector signs there. So let's look at the four different sides. At the sides, the AD and the CB, we have B is at right angles to ds. Outside the loop, we have B is 0. Inside, we have B is parallel to ds. So that gives us that the integral B times ds is inside the loop, so from A to B, it is just B times S times, well, B times ds, where S is now from 0 to H, so it is just B times H. The sides where it's at right angles is 0, and outside it is also 0 because B is 0. So we just have B times H. Now, if the solenoid has n turns per meter, then the amount of current inside that loop is going to be I times the number per meter times the length. And so we have B ds equals mu naught times the enclosed current, which is mu naught I times n times h. So we have B ds, which equals B times h equals mu naught I n times h. H's cancel, and we end up with B equals mu naught times I times n, where n is the number per unit of length.